So we have seen that there are four types of amplifiers based on the input and output impedances. So that will have consequences on the nature of the, or rather the topology of the feedback amplifier that we create out of them. To be more specific, the input and output impedance that will dictate how the feedback network is connected to the amplifier. So in this lecture, we will study what are the four possible topologies that can arise for those four amplifiers. And then we will derive the overall input and output impedance of the feedback amplifier. We had already carried out this input and output impedance derivation for one specific case of common gate amplifier, and we found that the impedances get modified in the desired way. That means new impedances is closer to the ideal desired value. So this time we will again carry out the same derivation, but this time it will be completely general. We will not assume any specific amplifier circuit. So first, because we have four types of amplifier, so actually there will be four feedback topologies. And they are Series-Shunt Feedback, second is Series Feedback, third is Shunt Series Feedback, and the fourth one is Shunt Feedback. So here each of these terms actually designate how the input side of amplifier will be connected with the feedback network output. So all these first terms, here you can say all the terms on the left hand side, so all these, they point out the nature of connection on the input side of the amplifier. While these two, all second term in this phrase, they designate nature of connection between amplifier and feedback on the output side. So we have these four categories, and all these four categories will be dictated by one of the amplifiers. So first type of amplifier that we will consider, which will lead to this series shunt feedback, is going to be the amplifier for which the input impedance is infinite and the output impedance is 0. So first topology, and this will be for amplifier where R in is infinite and R out is equal to 0. So this is the ideal case, but main objective of studying these four topologies is to find out what will be the overall impedance when the amplifier is no longer ideal. So this is for the ideal scenario, but we are going to study for the real case where Rin is going to be very large and Rout is going to be very small. And then we put this amplifier into feedback and try to see that what will be the overall input impedance resistance and overall output resistance. And here, since the input resistance is very large, so we know that on this side, this will be basically a voltage sensor. And on the output side, it will be voltage source. So the feedback network that we will connect to this amplifier will, what it will do is this beta network, it will on the input side, it will sense voltage. And on the output side, so this is the input of the feedback and this is the output of the feedback network, which we will connect shortly to the amplifier. On the output side, it will be a voltage source. Right. So since this feedback is going to act like a sensor, it will sense voltage from this amplifier. So we know that this connection of the feedback network to the output of the amplifier has to be in parallel. And that is why here we see that we have this shunt connection on the output side of the amplifier. And this feedback network on the output side is going to act like a source. And this source will be connected to the input of the amplifier, which itself is going to sense voltage. So this connection from feedback network to amplifier, this should be in series so that we can add the voltage produced by feedback to the voltage that it is already sensing from the external source. And that is why we see that this condition, that input impedance is very large or ideally infinite and output is very small, leads to this connection, series on the input side and shunt on the output side. And since on the both the input and output side of the final connection that we will evolve, voltages are involved. So input side is also going to be voltage, output side is also going to be voltage. So the another name of this topology, the series shunt feedback topology, that is also called voltage feedback. So all these four topologies, they can be named either in terms of the nature of the connection, whether it is series or shunt, or in terms of whether voltage is involved or current is involved. So in this case, we see that the amplifier that we have chosen is fundamentally a voltage amplifier. So both on the input and output side, voltages are involved. So this is voltage and voltage. So this is the story of the input side. This is the situation of the output side. So we can say that what we are going to consider now is voltage feedback. So here we have already considered the amplifier to be real. That means input impedance is very large and very small on the output side. But to keep the thing simple, initially we will consider this feedback network to be ideal. So we are going to take real amplifier, but we will take ideal feedback network. But later on, we will make this feedback network also to be real, and we'll see that what is the overall impact. So we are going to take real amplifier. That means it will have input impedance, and this is going to be very large. On the output side, it is going to behave like a voltage source, which will produce open circuit voltage VO and output impedance of RO. And this RO is going to be in general small. Now this is going to be fed back by a beta network. This is A. So we know that VO is A into VI. So here we have voltage. Here also we have voltage. So this feedback network is going to sense voltage at the output of the amplifier. So it should be connected in shunt. And we are going to consider beta as the ideal network. So the input impedance has to be infinite. And on the output side, it is going to act like a voltage source. So it will produce VF, and this voltage is going to get added to the input one. So the connection has to be in series. And this is where external voltage source will be connected to the overall amplifier. So this Ri of the beta network is infinite. R out of the beta network is 0. So for this case, now we want to know what will be the overall input impedance and output impedance. That means we want to treat this as a single block and then find out what will be the RIF and ROF. So this scenario gets simplified to this block. And this is going to be the overall gain, which we know that is going to be A divided by 1 plus beta A. So this we have already derived in the previous class. And these are the two things we have to find out. So let us first try to find out RIF. And we know that when we want to find out RIF, the setup that we have to implement is going to be following. On the input side, we take unknown source Vx, find out how much current it is driving into the circuit, and the output side is kept open. So RIF by definition is going to be like this. So keep in mind this is going to be valid when you have voltage, that means voltage amplifier. Input and output are voltages. We will see that for current amplifier, this definition will get modified. So now in this circuit, we have to find out what will be the input impedance. So we have to modify this circuit as per our definition. So what we will have to do is now connect unknown voltage here, Vx, and then keep this output side is anyway open. So we are keeping this output side open. Here, this is the circuit for which we have to find out input impedance. Right. So here first we will try to write a relation between this Vx and voltages on the input side. So we see that this Vx is equal to sum of Vi and Vf. So we start with Vx is equal to Vi plus Vf. And we know that this Vf that we see here is this input, which is Vo, because we have kept here the circuit open circuited, multiplied by beta. So this Vf is beta into Vo. So this equation 1 gets modified to Vx is equal to Vi plus beta Vo. Now this Vo, we see this Vo that we see here is modification of this Vi by factor E. So this Vo, or here we have already in fact written here. So this Vo, Vi plus beta A into Vi. So we see that we get Vx equal to 1 plus beta A into Vi. So now we have to get rid of this Vi and try to accommodate current Ix. So there is a current Ix that this Vx is driving into the circuit. So we see that this Ix actually flows through this Ri, and it is because of that this Vi is produced. So Vi is simply Ri into into Ix. So this says that Vx divided by Ix is equal to 1 plus beta A into Ri. So we had already taken Ri to be very large, and we see that and this is going to be RIF, the input impedance of the feedback network. So RIF is even larger. In fact, it is going to be much larger because this beta A factor is going to be typically very large. So this is going to be much larger than the input impedance of the amplifier alone. So this feedback network has fortunately pushed, or it has shifted the input impedance towards a more ideal condition. So this change that we saw for the common gate is actually desirable. So now we will try to find out output impedance. So for that case, we will have to modify this circuit as per the definition of the output impedance. So for output impedance, we know that we have to short circuit the input and then connect unknown voltage source Vx and then find out how much current it is driving into the circuit. So for ROF, this is the circuit we have to set up. Again, this is for the voltage amplifier. So we set up this circuit here. We have already done this, and then we try to find out what is Vx and Ix, or actually their ratio. Okay, so what we do is first we apply KVL in the input loop, in this loop. So when we apply KVL in input loop, what we get is Vi plus Vf is equal to 0, because this used to be equal to Vs, and Vs is equal to 0 now. So from here, what we get is Vi plus Vf is going to be input to the feedback network, and in this case you can see that this input to the feedback network is going to be actually equal to the external voltage that we have applied. So here what we have is Vx. So this Vf is now going to be beta into Vx. So this is beta into Vx is equal to 0. So Vi is minus beta Vx. Now what we will do, this is first equation. We will apply KVL in the output loop. So we now need to apply KVL in this loop 2. So here we can see that this beta network has no effect, because input impedance is infinite and it is connected in shunt. So what we will have only is this Vx, Vo, and voltage across RO. So what we will get is minus Vx plus RO into Ix plus Vo is equal to 0. And this Vo by definition is A into Vi. Therefore, minus Vx plus RO Ix plus A Vi is equal to 0. Now we can take the help of this equation number 2. So from 2, this becomes minus Vx plus RO Ix plus A into minus beta Vx is equal to 0. So here what we get is minus Vx into 1 plus beta A plus RO Ix is equal to 0. So this implies minus Vx by Ix is equal to minus RO divided by 1 plus beta A. So ROF, the overall output impedance, is RO divided by 1 plus beta A. So here RO was already very small. Now you can see that ROF is going to be even much smaller than compared with RO. So fortunately for the output impedance also, we see that the feedback network pushes the output impedance in the desirable or the ideal direction. So this is the advantage of feedback network. And this thing we have already seen for the case of common gate amplifier. Now what we are going to do is we are going to take the exactly different type of amplifier, that means current amplifier, and try to see that what will be the modification of the impedances. So we now take the second example of current amplifier. So we know that for current amplifier, the since it senses current, so the input impedance should be very small, ideally 0, and the output impedance should be very large, ideally infinite, and its transfer function or gain will be designated by AI. So now we have this type of amplifier. So let us take the model of this practical amplifier. So we have input resistance, but this is going to be very small, and on the output side we have ideal current source I0 and output resistance. So this on the input side it senses current, output side it produces current. So my feedback network, this will then has to sense current here on the input side. So we know that if it has to sense current, it has to be connected in series with the output of the amplifier. So connection is actually now going to be like this. Yeah. And for ideal current sensor, the input impedance of this beta network should be equal to 0. So we will assume ideal feedback network and practical this amplifier. Now on the output side, what we have to do is we have to add current here. The external current will be added, so it will be actually excited by a current source in this way. So current has to be added here. So on the output side of this feedback network, it should produce current. So on the output side, we will have the current source, and since it is a current source on the output side and current has to be added, so this has to be connected in parallel. Right. So we see that in this case, the input side connection is shunt, output side connection is series. So that is why this case is also called Shunt-Series Feedback topology. And in this case, current are involved. So this is also called current feedback topology. So here we have scenario which is exactly reverse of what we considered just now, some time back. And for this case, we want to know what will be the new overall input impedance. So that means we now want to treat these two or this big circuit as a single block, and then we want to know what is RIF and we want to know ROF. So and that means we have here overall block AF, and by the way this AF for this case also is going to be what we pointed out for the previous case. That means overall gain is going to get reduced by 1 plus beta A. But this time we have current amplifier, so the circuit that we will have to set up for RIF, ROF, they are going to be different compared with the previous case. So for finding RIF, we have to, of course, connect unknown current source IX, connect it to the input side of overall feedback, and but on the output side, we will not keep it open, rather we will keep it short. So this condition on the output side will be dictated by the nature of the amplifier, of course, but particularly by what should be the ideal load that should be connected on the output side. That decides what should be the load condition, whether it is current amplifier or the voltage amplifier. So for voltage amplifier, the ideal load should be infinite, then only you will be able to see whatever voltage is produced here internally. But for current amplifier, this RL should be 0, then only you will be able to see the entire current flowing here, right? So it is this idea which is used to find out what should be the condition on the output side of voltage or current amplifier. That means we want the entire output to be available or visible on the output side. So that condition should be implemented. And since it is current source on the output side, so it should be shorted. So this is the circuit that we will have to actually implement for finding out RIF. So RIF is going to be Vx by Ix. So now let us come to this circuit and try to modify it for finding out RIF. So here we have this circuit. So we know that there will be current here that we will call the input current. And there will be this feedback current, IF. And we know relation between IO and AI and the input current, and also between this current and the feedback current. So here what we will have is a feedback current. So this time you can see that this feedback is feedback network has this RIB is equal to 0. So it is like a short circuit. So this short circuit here actually is visible here. So it is visible here also. That means this IF that flows into this is actually going to be equal to this entire current that is being produced there. IU. So let us first try to write KCL at input side of the amplifier. So there we see that the external current that we have applied is equal to II plus IF. And this II is going to be uh, determined, or it's going to lead to a voltage across the input of the amplifier divided by Ri. So this II produces a voltage Vi here, or we can call it Vx also, because this Vi is the same voltage that we see here. So it will be better to call it Vx. So this is equal to Vx. So therefore, Ix becomes Vx by Ri into If. Now, this there's a mistake here. This is the input to feedback network, not IF. So this input to feedback network we see is equal to I0, and this I0 will then get modified by this beta to produce this IF. So here we see that IF is going to be beta into IIF, and this is equal to I0, this current that is being produced in the amplifier. So we can now substitute this IF also. This will be Vx by Ri plus beta into I0. Now we know that this beta in I0 is AII into the current that is flowing into the amplifier. And this II we have already seen here is equal to Vx by Ri. So we see that Ix is equal to Vx by Ri into 1 plus beta Ai, or Vx by Ix is equal to Ri divided by 1 plus beta Ai. So we have already seen that this is very small, and now this is the input impedance of the feedback network, RIF, and this RIF is even much smaller than compared with the input impedance of the amplifier. So we see that impedance gets modified in the desirable direction. Now we will talk about the output impedance. So here we have overall circuit, and this has to be now excited by unknown source Ix, and then we will find out how much Vx gets developed. And when this amplifier is used, it will be excited by current source on the input side, and ideal current source has infinite impedance. So that is why this time the input should be kept open. Recall for the voltage amplifier, this input side was shorted because for a voltage amplifier, this input side will be excited by a voltage source, ideal voltage source. And for ideal voltage source, we know that impedance is 0. So that is what for finding out the output impedance, this was shorted. But now it is going to, this is current source, so it will be excited by current source, and for that impedance is infinite. So this is what we will have to maintain for finding out ROF. So now let us impose this condition here on the overall circuit and then try to find out the uh, output impedance. So we excite using IX and then try to find out what will be Vx. So we have here zero current. This current is equal to 0, but there will be current here, II, and there is a IF current here. So at this junction, at the input, we see that the KCL will imply that these two are of opposite polarity. KCL at input gives II plus IF is equal to 0. It means II is equal to minus IF. And we have to find out IF. So here you can see that this IX, this is IX and it is coming from this feedback network. That means this I naught actually flows only through this R naught. It does not flow out of this network. So here we see that Ix is the current which is flowing into this feedback network, and that is why this IF is going to be beta into Ix. So this is minus beta into Ix, II. And we already know that output current is AI into the current that is flowing into it. And on the input side, we have already seen this. So this is AI into IF. Now we apply KCL at output. So here we apply KCL here at this point. So what we have is Ix current and current through, there will be some current through this IO or RO. So this Ix gets splitted into this IO and the current through this RO. So KCL here gives Ix is equal to IO plus current through resistor. IO we know is AI into II, and this is going to be Vx by RO. So voltage across RO is going to be Vx, because here you can see that this terminal is short circuited. So this voltage is same as this voltage. These two nodes, they are already short circuited, but because of beta network, these two nodes, they are also short circuited. Yeah. So what now we have to do is, so this implies Ix is equal to AI, and this AI is, we have already seen from the feedback relation, is equal to minus IF and IF we have seen is equal to beta into Ix. So here we have Ix into 1 plus beta A is equal to Vx by Ro. So Vx by Ix is equal to Ro into 1 plus beta A. So for practical current amplifier, we have seen that this is already large, quite large. So this new output impedance ROF, this is going to be much larger than RO. So this is again modification in the direction of the desirable value. So here we see that even for series, that means current case, the modification of the impedance is in the desirable direction. So now we can extend this idea, and we can say that even for the other two classes of the amplifier, that means series case, the impedance will get modified in the desired direction. So here series means on the input side, what we have is voltage. That means the Ri will be normally very large. So the overall RIF should be still larger. So that is why the new impedance is going to be Ri into 1 plus beta A. So we can straightway write, based on these two cases, what will be the ROF. So now here on the output side, we have series connection, right? That means on the output side, we must be tapping current. We must be dealing with current. So amplifier must be producing a current, or it should be like a current source. So that means the feedback network, it must also be sensing the current. Its input impedance should be small, but the output impedance of this amplifier, the original amplifier, should be very large. So that means the modified output impedance, that should also be large. That means this should be the overall output impedance. Now, if you talk about the last case, which is the shunt case. So on the input side, we have shunt connection. That means we must be having current input in the amplifier. That means Ri should be very small. That means the overall impedance should now become even smaller. So in this case, the overall impedance will be like this. On the output side, we have shunt connection. That means we have voltage as the output of the amplifier. That means RO must have been very small or must be very small. That means the modified impedance, it should be even smaller. So we see that by simply knowing the uh, nature of the amplifier, which is put in the feedback, we will be able to write what will be the overall input and output impedance. So this is assuming that feedback network is ideal. So one would like to know that what will happen if we make a feedback network also to be practical. So we will return back to the first example that we discussed. That means series shunt, that is voltage feedback topology with realistic feedback network. So we now have real feedback circuit. So let us see that what will be the overall circuit, and then what will be the overall impedance. So here we have our amplifier. So this is series, that means it is voltage. So we have RO A, let us call it ROA, RIA, and we know what should be their value. Now the feedback network itself is practical. That means it will have certain input impedance. Earlier, this input impedance RIB was taken as infinite because this was supposed to sense the voltage in parallel. So this RIB was taken infinite. Now it will be finite. And the output side, we had earlier only voltage source VF, but now we will have a voltage source with certain impedance, say R, O, B, that of the feedback network. And this will be, of course, connected in series like this. So here we now have a beta network which is real, and we have a voltage amplifier which is also real. And now we want to know what will be the overall input and output impedance. So we want to know what is this RIF and what is going to be this ROF. And especially we want to know whether these modification will be in the desired direction, or it will improve, or it will degrade the previous scenario. So here also one can carry out the uh, analysis. Analysis is not going to be very difficult because here you can see that this ROB and this RIA, they are actually in series, right? So what one can do is one can simply remove this impedance from here and assume this ideal condition on the output side of the beta network and modify this input impedance of the amplifier and say that this is Ri, and this Ri in this case is going to be RIA, the input impedance of amplifier, plus the output impedance of the feedback network. So we can take a new impedance or the resistance for the amplifier, and the output side has become real. So input side situation gets simplified very easily. But on the output side scenario is going to be not so straightforward. So here also we can remove it, because you can see that that connection was actually this RIB is connected in parallel with the output. So this is in parallel with the output. So this RIB can be removed from here, and then it can be connected here. Now you can see that this RIB basically acts like a load. Up till now we have been considering open circuited or infinite load here, but the input impedance of feedback network behaves like load here. So this is the circuit, and we have been able to reduce the beta network to ideal, but on the output side scenario is no longer ideal. We have a load, and one can repeat those steps that we took for the previous case to find out the new input impedance. So here also we will have to set up this circuit. Vx, find out Ix, but this time actually there will be no true opening, and here we see that we have RIB. But we can absorb this RIB here internally, and then we can say that we do not connect any external load here, although RIB is itself like load. So if you carry out this analysis, the new feedback impedance will be like this: 1 plus beta A into RIB divided by ROA plus RIB whole into RIA plus RIB. Right. So if you recall the previous case, the ideal case, then we had 1 plus beta A into RI. So here we still see that the input impedance or resistance of amplifier is getting multiplied by 1 plus beta A factor, but there is another factor here. And this factor, you can see that it will be close to 1, because the here we see that the input impedance of the feedback network RIB, because it is sensing voltage, is very large, and the output impedance of the amplifier ROA is very small. So this factor is going to be close to equal to 1, although it will be smaller than 1. So there is a slight reduction here because of this factor. But here you can see that on the in the different factor, the second factor, we have RIA, which was actually RI, the input impedance of amplifier. Now we have impedance of the feedback network added, and this is going to be large. So here we can see that on the whole, this is large. So we see that even with a practical feedback network, the scenario is favorable. It is in the direction in which it should be. Similarly, for the ROAF, where we will now connect external voltage source, keep the input side shorted, and find out this ratio. So ROF is Vx by Ix, and here of course we will keep RIB. RIB has to be there. This cannot be removed. So in this case, if you carry out this analysis, so what we will get is ROE, the output resistance of the amplifier, which was supposed to be very small for ideal amplifier. When it is put into feedback, what we will get is ROA divided by RIB plus 1 plus beta A. So for the ideal beta network, this was Rho divided by 1 plus beta A. So we see that scenario is still similar to this ideal case because 1 plus beta A's factor is in the denominator. Numerator is ROA, which is very small. And then we have this additional factor, but this factor is also going to be small, positive. So we see that ROF on the whole, it remains very small. So this feedback network has not degraded the output impedance performance of the feedback network. It has still maintained the desirable quality. See Rajavi. Or you can see Gray and Mayer also.